Perfectly.
Okay, so hi everyone. I present this work together with Feixiong Huang of the Purdue University, Stoffelen from the Royal Netherlands Meteorological Institute, and Marcos Portabella from the Barcelona Expert Center. So why we did go through this study? Basically, GNSS-R derived winds have low impact on weather forecasts. Why that? First, there is an intrinsic cause. So as you can see in the image on the right side of this slide, this represents the curve of the normalized bistatic radar cross-section with respect to the wind speed. So when the wind speed is higher than 8-10 meters per second, the curve is rather flat. This means that you have low sensitivity to these wind speed regimes. And this is an intrinsic cause. After that, the authors of the paper that you can see at the bottom of this slide have verified that for what concerns the mission Cygnus, which means cyclone GNSS, the 8 receivers that constitute this mission suffer from intercalibration issues, and they resolve the problem by means of an intercalibration, a trackwise intercalibration procedure. And they show that this improves a lot the retrieval. But we have thought also that as the routine algorithms for the retrieval of the wind speed only exploit one part of the DDM that is around the specular point, we think that a multi-look approach can improve the retrieval. And this is the core of the presentation that I'm going to show you today. So we did apply 2 different multi-look approaches, the first one of which is the 2D variational assimilation model. In this case, I won't go through the methodology because I would give you lots of details. So for the sake of brevity, I just give you information about the dataset. For the people that are interested in this methodology, can refer to the paper that is cited here at the bottom of this slide. So the period of this data set is June 2017. We collocated the Cygnus version 2.1 DDMs with the scatterometer measurements of the ASCAT-A and HY2B missions, and together with the wind field from the ECMWF forecasts. According to these 2 spatiotemporal constraints, so the acquisition time is within 40 minutes, while the maximum allowed distance is 25 kilometers. And after the quality control, we have more than 660,000 triplets. The results are shown here. So on the left plot, you can see the scatter plot of the original ECMWF wind speed versus the scatterometer wind speed. You can see that the bias is almost null, while the RMS is 1.17 meters per second. When you apply the 2D VAM methodology and you obtain a blend of the ECMWF with the, let's say, the DDM information, you have a consistent reduction of the RMS that amounts to about 15–16%. So for what concerns the star processing, this is the other methodology that we applied. So the star processing, the study that we have done takes inspiration from the paper that you can see at the bottom of this slide. So if you are interested in more details, you can refer to this publication. So basically what happens in this slide, you can see 3 plots, the left one of which represents a typical DDM, so delayed Doppler map, which is the typical acquisition of GNSS-R receivers from satellite, which represents the typical DDM acquired over the sea surface. And you can recognize it by means of this typical horseshoe shape, which is also recognized as the ambiguity-free line. So what is typically done, if you can see my pointer, basically both TechDemosat and Cygnus mission use this part of the DDM. So a single look approach, they average this information, so this 5×3 beams around the specular point in order to retrieve the wind and throw out all the remaining part of the DDM. Of course, this is this can be optimized in our opinion, because if you consider a target area, for example, which is represented by the cyan bullet on the right side of this slide, you can see that this cyan bullet is mapped onto 9 consecutive DDMs that you can exploit by optimally averaging this information. Of course, you can apply at least two different methodologies of star processing and even more, but in our case, we did apply these two. So in the bottom right of this slide, bottom right plot, you can see the cyan bullet and the bin to which it belongs is mapped into this red framed bin. While if you consider an entire target area of about 25 by 25 kilometers around this target area, you will have that the bins that are interested by this target area are mapped into these black framed bins on the left side. And the images that you can see on the right side are the correspondent Woodward ambiguity functions, which is basically the space response function of the instrument. And overlaid to these plots, you can see also the isodelay and isodoppler lines, which are respectively represented by these elliptic lines and the straight lines. So I will start now an animation just to let you know more about this, what I mean by that. So I don't know how to select this one. Okay. Now, in this animation, you can see how this target area, can you see the animation? Excuse me, Andrea.
Yes, we can see.
Oh, yes. You can see that in this animation, the target area is mapped into the 9 consecutive DDMs that I told you about before. So the aim is that of exploiting all these looks, if you want, in an optimal way in order to reduce the noise on the observable. So I stop again and come back to the presentation. So, okay. So this is the effective sounded areas. So if you consider a multi-beam star processing approach, of course, you have a larger effective sounded area. The cyan line here represents the -3 dB effective sounded area, while the magenta line represents the -10 dB. And this dashed line, red dashed line, represents our target area, so 25 by 25 kilometers. Of course, if you apply a single beam approach, the effective sounded area will be much smaller than in the other case. Of course, in the first case, so in the multi-beam star processing, you should expect a better averaging because you average more information. You should reduce the noise with respect to a single beam approach. So the data set that we used for this application spans the period from June to August 2017. Again, these Cygnus 2.1 DDMs are collocated with the SCAT measurements and the ECMWF forecast wind field. The spatiotemporal constraints are the same that we used before. We applied the intercalibration factors by NOAA, and we underwent a quality control, which is the quality control of the Cygnus DDMs, the one from the SCAT measurements, the NOAA quality control, and one that we specifically designed for Cygnus and Tech Demosat DDMs that I mark here as QC KNMI because it was done at KNMI during my fellowship program. And if you want to know more about this quality control, you can read these two publications that are cited at the bottom of this slide. And we have almost 400,000 triplets. So this is a preliminary result. So in this slide, in this plot, you can see the sigma naught obtained with the single look approach. So the DDM average, that is the observable that Cygnus and TDS-1 staff use for their retrievals. And this is reported in blue. You have in red the equivalent time series of the sigma naught obtained with the single beam star processing, while the green curve represents the one obtained with the multi-beam star processing. On the x-axis, you simply have a time index, okay? It's not second, it's not minutes, it's just a time index. So you have this time series extracted from June 2017. And overlaid, you have also the corresponding time series of a wind speed, which is depicted with this black curve, the axis of which is reported on the right side. And you can see that two things are apparent in my opinion. So first of all, you have an anti-correlation between the sigma naught and u. And this is to say that the larger the wind speed, the lower the sigma naught is. And this is expected because this is a bistatic radar configuration. So the higher the wind speed, the higher the scattering on the sea surface, and the lower is the echo received by the GNSS-R receiver. And the other apparent thing, is that the green curve is smoother than the red one, which is smoother than the blue one. So this is to say that the stir processing, so this multi-look approach, reduces the noise. So in conclusion, the 2D VAM gives good results, and even the stir processing seems to be promising. Indeed, we have at least a 5% reduction in noise. We have good improvement, especially in low U ranges. And for future work, we will retrieve wind speed with the two methodologies of stir processing shown here, and we will validate the retrieval. So in my presentation, I want to acknowledge EUMETSAT because this work has been carried out in the context of a EUMETSAT fellowship, the name of which is a GOODY, so GNSS Observation Operator Development and Impact Evaluation. The people that are interested in this project can visit the link at the bottom of this slide. So for me, that's all. And if you have any question, please just ask. Thank you for your attention.